QUVIK mission. Here is a pointer. Do you prefer handheld microphone or you need
I think I can take it.
So, please, Michal, the stage is yours and your presentation is appearing now.
Yes, thank you very much. So originally, in the original program before the floods, my talk was 4th or 5th. So if I knew it will be the first talk, I think I would maybe adjust it a bit, because my talk is on active galactic nuclei and related Czech mission, Czech Space Telescope QUVIK. And of course, there are many relations, as I will show, to outflows. So we have, of course, multi-component outflows from AGN, and this is related to galactic outflows. And of course, in galactic nuclei, we have also nuclear star clusters. So this is also related to IMF problems. So I will, of course, try to provide some bridges to the main themes of the meeting. And I'm here a representative or a member of a local astronomical community from Masaryk University. So let me. Actually, this is the old version of the talk, because I did in the meantime some adjustment, but I'm not sure, Teresa, if it's possible to still switch to, because there were some other additional slides. Sorry for that. Yes, so yeah, so in the meantime we can admire the logo, which is actually very nice with all the instrumentation and galaxies. Yes, yeah, it's that is one. Thank you. Great. So yeah, because I wanted to, of course, welcome you here in Brno, and specifically on this place, Kravy Hora, which so in these days it's quite rainy and indeed with some flooding in Czech Republic. But this is actually nice photo from the summer, from July, taken by Pavel Gabsdil, who works here at the planetarium, and this is how it can also look like here during the festival of planets with many people. You see the castle downtown, and I hope by the end of the week there will be more sun and you can explore this nice city. Yes, and to introduce our group, so I'm a member of High Energy Astrophysics group, which is led by Norbert Werner, who is also here, and I think will talk by the end of this conference. So this is the whole group, and we have several people who actually work on galactic nuclei. So this is like a smaller group or a subgroup, and we are working on problems of the galactic center on one hand, which is a representative of extremely low luminosity AGN, but then also we have several projects on highly accreting sources, quasars, and also sources with intermediate accretion rate, so spanning the whole parameter range. But so the main focus of this talk that I should introduce project or space mission, QUVIK, so Quick Ultraviolet Kilonova Surveyor, which is a which is going to be a UV space telescope that was approved for funding by the Czech Ministry of Transport, also in collaboration with the European Space Agency, as a part of ambitious Czech national space mission program. And the primary scientific objective will be to capture UV emission of kilonovae, so following the mergers of neutron stars, and it's this UV emission peaks shortly after the merger, so the QUVIK, as the name suggests, will be quick, so within 20 minutes it should redirect on the source. That will be, of course, triggered by gravitational wave detectors, and we'll search for this UV emission. So this is by itself a very interesting and still relevant primary scientific objective, because currently there are many uncertainties and unknowns about this UV emission. What is the exact process? Although, of course, the basic theory is there, which has been done already by Bogdan Paczynski, Brian Metzger, and others in the past, that which is connected to our process, and basically the production of heavy nuclei and subsequent radioactive decay that powers this UV emission. But of course there are still many parameters and unknowns that need to be constrained. And secondary objectives, because of course there is still quite an uncertainty concerning the number of kilonovae within a given cosmological volume. So QUVIK aims to in near UV to aims for the photometric sensitivity of the 22nd AB magnitude with a signal-to-noise ratio 5 in about 900 or 1,000 seconds. Of course, in this sense, the sensitivity is limited, but there are, of course, several other targets that, in the meantime, while there is no kilonova, QUVIK can observe, and these are, of course, hot stars, supernovae, star clusters, gamma ray bursts, and of course, a traditional source in UV astronomy are active galactic nuclei, or galactic nuclei, which, of course, the activity can increase. And concerning the technical setup, so here is actually the current illustration, and with the optical system outlined. So it will be a modified Cassegrain with the diameter of the mirror of 33 centimeters, with the field of view of 1 square degree, and the point spread function of about 2.5 arc seconds. So in this regard, it will be more suitable for dedicated UV observations in comparison with the planned ultrasat mission, which will be survey mission with a very large field of view of about 200 square degrees. And the plan of QUVIK, also in contrast, for instance, with ultrasat, is to have 2 photometric bands, near UV from about 260 to 360 nanometers, and a far UV band from 140 to 190 nanometers. So the goal is basically to have 2 bands that will bracket the ultrasat band. So in this sense, there will be for some targets that ultrasat will capture. So the follow-up observations by QUVIK will provide extra photometric information, which will, for instance, enable to distinguish between supernovae that evolve relatively quickly in color and tidal disruption events that have approximately constant color. Yeah. So currently the mission is in preparation, both on the scientific side and technological side. So there are still many details to clarify, and in the meantime we have been trying to list and specify the scientific program, And we summarized the main analysis in 3 quite extensive review papers published in Space Science Reviews, which was a special issue on QUVIK. So there is a paper on mission description and stellar transients led by Norbert. The second paper is on observations of stars, stellar systems, led by Professor Kritička from our department as well. And then active galactic nuclei and nuclear transients, which was led by me. So for more information, because I will just give, of course, very superficial information, you will find more information there. So this is the scheme in detail. So this is the model, but actually we have the model here somewhere. It's a bit hidden, but I think we can reveal it. So I think during the break you will have more time to to appreciate the model and investigate. Yes.
This is 3 times smaller than the real one.
Yes. Well, that's
The real one is the size of a washing machine, as I usually say.
Yeah. And so it's current design is rather modular. So there are these modules, about 6 modules, and so in the current design there is a cover, and this is the payload module with the telescope. And actually I showed already the this is one of the possible optical designs with the near UV detector here and the far UV detector in this part. Yes, and so concerning galactic nuclei, so of course we plan to monitor selected active galactic nuclei, so to perform photometric reverberation mapping, so to basically detect the delay between near UV and far UV emission and other wave bands. And then also it will be possible to provide follow-up observation for nuclear transients, so mainly tidal disruption events, but also to monitor selected changing look AGN and other peculiar sources. So this is basically shown here. So the survey missions, like for example LSST, Ultrasat, or Zwicky Transient Facility will provide triggers to basically that can be observed then by QUVIK. So these are mostly nuclear transients, tidal disruption events. And of course then we will have also dedicated monitoring program on reverberation mapping, photometric reverberation mapping, or to do special campaigns also with X-ray instruments and optical instruments. So I should probably say that a significant fraction of the time will be actually dedicated for follow-up observations of Ultrasat targets, but then there will be also approximately 50% of the observational time that will be open to the community, at least in the current setup, roughly. So this will be then open for proposals. So there will be proposal program and selection, and the data after some time should be then available to the whole community. Yes, so in terms of the sensitivity and AGN detection, actually QUVIK with the sensitivity threshold of 22nd magnitude in near UV, that's sufficient to detect actually a quite large number of quasars. So these are basically redshift limits and magnitudes, and you see that the numbers are quite substantial, and also the signal to noise ratio that can be achieved within the integration time can be achieved is quite large. And of course then the actual luminosity, so this is an exemplary calculation of the magnitude versus frequency. So here are the target UV bands. So then the luminosity depends on the redshift, the black hole mass, and also the relative accretion rate. So here is in Eddington unit 0.1 and 1. But overall there are good prospects to detect BRI bright quasars up to intermediate redshift. And of course, for the monitoring program, we aim to do reverberation mapping, which most of you probably, of course, know that reverberation mapping swaps spatial resolution for temporal resolution. So since we have only very few targets, very few galactic nuclei that we can resolve with large interferometers, like of course gravity interferometer has resolved some broadline regions of nearby quasars, and then EHT has seen or provided spatial information on galactic center and M87, but these are still very few targets. So then reverberation mapping allows us basically to map the vicinity of supermassive black holes for a larger number of sources. So currently, in terms of reverberation mapping of broadline region, so that has been possible for several hundreds of targets, and of course with employing also photometric bands, like using photometric reverberation mapping, we can potentially extend it to also using LSST and other programs. To this number will likely exceed thousands of sources, that where some information on the spatial scales will be available. So of course, in terms of UV optical reverberation mapping, we are probing the region between 100 to about 10,000 gravitational radii in terms of the gravitational radius of the supermassive black hole. Of course, employing other wave bands, one can then map together with X-ray the region from the very close vicinity of the supermassive black hole to if one goes to infrared bands, then one reaches also the dusty molecular torus. Of course, the larger these scales, then it takes longer and longer, and it's being also increased for higher redshift sources. So then reverberation mapping programs, of course, can take quite a long time. But in UV domain, it's not so bad. So actually, here is the basic prescription that, of course, we have some driving ionizing radiation, which can be X-ray corona, and then this radiation is reprocessed by the accretion disk in far UV, near UV, and optical domains, and basically this reprocessed emission is then delayed, and this delay is approximately given by the light travel time. And here is also the transfer function of the accretion disk, which causes the delay of this ionizing driving emission, and also it's being blurred. So here is basically for QUVIK and the spatial scales that we target, and the black hole masses between 10 to 7, 10 to 9 solar masses, the times basically that are of interest, that basically give an idea how long such a monitoring of a given AGN should last. So basically for 10 to 7 solar masses supermassive black hole, it's of the order of a few days, while for very massive supermassive black holes, it can be, of course, several tens to hundreds of days. And we did some experiments in terms of this reprocessing by the standard accretion disk. So this is basically an example of such a variability, typical variability in active galactic nucleus. And so we tried different cadences and supermassive black hole masses between 10 to 7, 10 to 8 solar masses. And the light curve of the driving ionizing radiation, or X-ray corona, so that was calculated using Timmer-Kernig algorithm, assuming certain power density spectrum. And then basically we, assuming the model of the standard disk, we did some mock tests or mock observations of what cadence and emission and reverberation mapping duration is necessary to actually capture a significant time delay between near UV and far UV bands. So, we found that for 10 to 7 solar masses supermassive black hole, 10-day monitoring is actually sufficient, but the high cadence of about 0.1 days is then necessary. For 1 order of magnitude larger supermassive black hole, cadence can be lower, of the order of 1 day, but the observation should last longer to give us significant constraints on the time delay. So we are basically considering, we were calculating the light curves of the ionizing radiation and then the delayed and blurred reprocessed emission in far UV, near UV, and we were calculating the time delays using interpolated cross-correlational function and chi-square algorithm, and then we basically could tell which program for which sources, given the supermassive black hole mass, is the best to actually detect a significant delay between near UV and far UV. Because this in a UV, this is actually not so well constrained, and this then gives actually the information about the length scales in the accretion disk itself. So it's basically possible, given these kind of observations, also incorporating other wave bands to test accretion disk models. What is the actually temperature profile in accretion disk? So this is quite relevant, and there are still many issues where standard disk like Shakura-Sunyaev disk does not seem to quite capture such observations, but there are very few data in a near UV and a far UV, so QUVIK can then help in these aspects. Yes, and when of course we want to link it to effect of outflows, so of course when we have this driving ionizing radiation corona and standard disk, so these are of course not the only components in galactic nuclei. There are also more extended media like the broadline region, but also the extended medium related to outflows, which in a galactic nuclei, I think there will be more talks on these aspects, have many components with different velocities and ionization parameters, and of course this should be taken into account because of course this can lead to the prolongation of the, also in the photometric bands of the actual time delay. So here is the example when we have the delay versus wavelength, and for this is redshift 0, so these are the basically far UV and near UV bands. So this is the time delay which is expected only from the disk contribution, but the more extended medium like BLR can then prolong the measured time delay, and of course then in principle, without, of course we can do this theoretically, like to include it in the transfer function, this extended medium, in addition to accretion disk, but of course when we measure a particular source, we don't know what is the contribution of this, so we just measure certain time delay. So in the post-processing or basically disentangling, it's important to disentangle the contribution of different components in AGN, so the disk and extended media. So this is basically, in this work we need, it's basically synergy between high cadence observations that will provide this information and more exact models of active galactic nuclei. Yes, and concerning nuclear transients, which of course QUVIK can then increase the number of studied tidal disruption events in near UV, far UV. In this regard, there is still an unknown origin of UV emission in tidal disruption events. So of course there is, after the optical peak and optical outburst, there is actually also shortly or almost simultaneously there is UV emission, and then several weeks afterwards, typically with some delay, X-ray emission appears. And so the origin of UV emission in this regard is currently not exactly constrained, so it can be due to shocks at apocenter or more discrete interactions between streamers that return and interact with the original debris, or it can be also due to viscous fluctuations that propagate on the local viscous time scale in elliptical-like disk. And currently there are papers that discuss shocks and also some papers that discuss elliptical disks. So I think in this regard it's important to have a larger number, larger statistics of tidal disruption events to constrain this more. So in most TDs, actually what is detected is, as I mentioned, that optical UV are first, and they are followed by X-ray emission, which is interpreted as due to circularization of the debris and formation of small compact disk close to the tidal disruption radius that is then being consumed by the supermassive black hole. On the other hand, some models also discuss the reprocessing, because of course once there is an X-ray emission after the TDE, this X-ray emission can be further reprocessed by more extended medium, where again the winds, because this extended medium in galactic nuclei is not really stationary, never quite stationary. It's either an inflow, outflow, and these structures, of course, coexist. So this is important to keep in mind. Then, of course, we potentially high cadence monitoring of TDs can also reveal some quasi-periodic flares or eruptions that could be related in some cases to lens steering precession of the formed disk, and from the precession period, and adopting some parameters that sometimes can be constrained for some tidal disruption events, one can then give some constraints on the spin of the supermassive black hole. So using nicer data, actually, we recently did such experiment with the spin constraint for the source 80 2020 OCN, which was where the eruptions were detected by NICER using high cadence X-ray monitoring, but also in principle in UV such observations are relevant. And here is the example how the precession period then depends on the spin of the supermassive black hole. Of course, there are other parameters like the surface density profile of accretion disk and outer radius. But in principle, for a large number of such detections of initial variations after the stars is disrupted, because the origin of these variations is because the flow is formed in a misalignment with the equatorial plane. So then you have basically this, due to drag of the space-time, the disk is precessing, but at some point it aligns to the equatorial plane and the precession stops. So that's why it's also important to capture these events early. Yes, and so for more such detections and constraints, of course, then in principle it can give information also on the evolution of supermassive black holes, because high spins typically mean that black holes grow by accretion in some preferred direction, while low spins can indicate more the contributions of mergers from rather random directions. And then, of course, QUVIK can also try to capture some low luminosity AGN in the nearby universe, where it can help to constrain the spectral energy distributions of low luminosity AGNs. Of course, here the problem is that there is contribution of starlight from the galaxy and the bulge region, but for relative accretion rates between 10 to minus 3 and 10 to minus 2 of the Eddington ratio, in principle, the contribution of accretion flow for advection dominated accretion flows could still be higher than the starlight, as we were comparing here for some exemplary cases. And then, of course, most interesting discoveries can be those that are not really predicted by standard textbook theories, and this can be certain classes of repetitive transients. So I mentioned some, like due to potential lens steering precession of accretion disk. But actually, in the anticipation of future gravitational wave observatories like LISA towards lower frequencies, transients, nuclear transients, repetitive nuclear transients are of interest to capture candidates for extreme mass ratio in spirals. And in that case, we could have electromagnetic counterparts also in the UV domain to these MRIs, extreme mass ratio in spirals. And actually, this could be also interesting as part of the process for the hunt of intermediate mass black holes, because as we show here, for certain inclinations, as such an intermediate mass black hole passes through the accretion disk around supermassive black hole, it can have a temporary accretion disk, and this can lead to UV flares that actually exceed the quiescent emission of the primary accretion disk. So this could lead to repetitive UV outbursts that basically would repeat on the orbital timescale of this smaller black hole. So this is another potential. These are potential targets also for QUVIK in this transient category. Of course, such sources, if detected, they should be relatively stable. So then, of course, from transients, they would also could be monitored after the detection. So this is then, of course, generally relevant also in the anticipation of gravitational wave events. Yes, and when you ask me about more generally about outflows from galactic nuclei or AGN, so of course QUVIK as a photometry mission is not perhaps that interesting for you, but there are other missions. So I gathered some information on other missions in preparation, and I think I consulted with some colleagues. Actually, they told me that the best is to have simultaneous UV and soft X-ray high resolution spectroscopy to basically capture this rather complicated structure of AGN outflows. So you see that from the innermost region you have ultraphase outflows, then in the broadline region you can have related outflows with broad absorption lines, and then further out warm absorbers that are detected in X-ray by colleagues here. And so the structure can be generally complicated with different components, with different velocities, ionization parameters. And actually, here the colleagues performed some experiments, for example, for NGC 3783, that such a mission, which actually is in preparation, is called Arcus mission, that should have both UV spectrometer and X-ray spectrometer. So then, in UV, it should detect absorption due to O6, broad O6 absorption, and then in X-ray, in soft X-ray, it can detect O7 absorption, and together when combined, so simultaneously, then it's possible to constrain much better the properties of these outflows than from individual X-ray and UV observations. And actually, it's important to do simultaneous, especially for changing look AGN, because as they can change the state quite quickly. So of course, then from unobscured to obscure, there can be profound changes, which with not really simultaneous observations can be somehow blurred. And this is just a comparison that such a mission, if the sensitivity is 5 times higher than for HST UV detector and 50 times larger than XMM RGS, then it can nicely detect these broad absorption features, O6 and O7. So blue is the Arcus simulated detection of these features. And then when combined, it can actually nicely constrain the column density and ionization parameter of these related outflows in AGN. Yes, and of course it can also map given the time, integration time, and so this is for O7 region. It can constrain generally the density and kinetic power much better than for current RGS spectra. So in this sense, the combination of UV and X-ray spectroscopy to really map these complicated outflows seems the most promising, and also it can provide constraints with relatively small uncertainties up to the intermediate redshift with 200 kilosecond observations. So this is quite interesting, but of course then one needs really the UV spectroscopy in combination ideally with X-ray spectroscopy to do this kind of precise constraints. So let me summarize these contributions, which was somewhere on the verge between instrumentation, which is the Czech instrumentation in preparation, and AGN science. So with missions such as QUVIK, we can do in the future also simultaneously with other wavebands. We can do reverberation mapping of accretion disk between far UV, near UV, and other wavebands, which can provide us constraints on the accretion disk size and temperature profile. Then, of course, we can obtain significant results on the origin of the TDE UV emission. We can also probe some non-standard accretion like low luminosity AGN or changing look AGN, or potentially some binary sources. And there can be, of course, also some not really expected discoveries, but maybe some quasi-periodic phenomena or just temporary quasi-periodic phenomena, as we see actually nowadays in X-ray, like the X-ray quasi-periodic eruptions. So there could be also some UV quasi-periodic eruptors. And concerning outflows from AGN, so UV photometry, we can only indirectly detect or basically such outflows, and this can lead to the effects of prolongation of continuum time delays. So that should be indeed taken into account. But of course then to really trace the outflow structure with different components, high resolution UV spectroscopy is needed, and I showed the example for the future Arcus mission that there is already some preparations of such mission. So thank you very much, and I'm looking forward to your questions. Thank you.
Thank you, Michal. Questions? We have Matej here, and he will run very fast with the microphone to you.
Very nice talk. I was curious about the spectral resolution of this Arcus mission compared, for example, with GRISM mission.
Yeah, I think maybe then other colleagues can come. I just know that it should be, in comparison with XMM, it should be about 50 times more sensitive, and in soft X-ray, as also demonstrated here. But I think on GRISM there are other people that are involved, so maybe they can comment.
Thank you.
Yeah, sorry, but I'm. This was just an example because I thought that it's nice to edit, because of course the organizers asked me to talk about QUVIK, but of course QUVIK is then, as I only showed, it can only indirectly, the outflows can be only somehow indirectly influence the observations in terms of time delay.
I was pointing at you.
Oh, okay. Yeah, thanks for the talk. I'm mostly interested in a satellite itself. You didn't say much, like launch date, which vector, which orbit.
Yeah, sorry, because we are discussing about it all the time, so maybe I thought that it's somehow well, we know it, but of course others don't know it. So I think the planned launch date is in 2028, 2029. So in that window, to still be to still observe simultaneously with 05 run of LIGO, Virgo, Kagra interferometers. So in this sense, because these will provide important triggers for, especially for the primary objective, which are kilonovae, and orbit should be so low Earth orbit, so about 550 kilometers, the dawn-dusk orbit, and so maybe if there are others involved, I think Lydia here or Norby, which I think is somewhere close to the light, or so maybe they can add more information. Yes.
If I may, also you have a range of science topics. So did you already decide about the observational strategy? Would be like survey time, dedicated time allocation, or any ideas?
Yeah, as far as I know, so there was recently we also signed a memorandum of understanding or collaboration with Ultrasat. So 50% of the observational time should be used as a follow-up for Ultrasat targets, so mostly transients. So then the rest should be basically should be open for the competitive selection in terms of proposals. I think there was also some discussion concerning involvement with LSST, so that's part time could be used for LSST targets. But maybe if I somehow confuse it, others can correct me. But yeah, that should be roughly the idea concerning the observational strategy.
Okay, thanks.
If not, then let's thank Michal again.
Yeah, thank you very much.
And we will proceed to our next speaker, which is Pavel Jachim from the Czech Academy of Sciences, and he will speak about ALMA and the Czech ALMA arc and some related observations. Are you okay using the handheld mic? Yeah, okay.